Hey everyone, I'm Freddie, I'm your tutor for this year, and today we'll be looking at backtracking. So what is backtracking? I've got two examples here. Example on the left is a flow diagram I've made of a general backtracking algorithm. It's a bit more abstract. And then the one on the right is more of a simple network that just has arrows and pictures. It's very simple. So the one on the right is kind of an example of DFS. So we start at the start node on the very left when we're doing DFS, and then we'll just guess that the first path that DFS has gone down is the middle. So as DFS goes through, it's got to that middle node, it still has other ways to expand. So in backtracking, you need partial solutions as you go along. And then as it's gone to the next node, the red node, DFS can't search anymore because there's no more nodes to expand. So that node is marked as closed, explored, finished, anything you'd like. And then it moves back until it is in a problem state that it can expand more. And you can see the arrows of the direction it's gone back, and it goes back to the start. So when you go back, sometimes it's done through a stack or it's done recursively. Recursive is also a call stack anyway. So we go back to the start, and then we can explore other directions. So the diagram is noted that the top and bottom are also solutions. But yes, very generic. I'll show you some examples. So this example here is DFS on a figurative maze. So this figurative maze, we enter through node 0 and we exit through node 4. Each node is an abstract, it's an abstraction of an intersection. Each part of the maze where you need to make a decision. So we start at node 0, and then we can either go to node 1 or node 4. And that is that correlates to did we solve G on the abstract diagram on the left, and G being have we completed and exited the maze. Next one please, Fred. So DFS on this maze has taken us to intersection 1, and from intersection 1 we can go to node 2 or node 3. And we'll just go to the next one. So DFS goes to node 2, and then from node 2 we're met at the did we solve G decision again, and from 2 we either are we at a dead end, did we solve it, or we didn't solve it, and we're not at a dead end. So from node 2 we are at a dead end. So when you're at a dead end in backtracking, you go back up your call stack or back up your problem states until you're at a state that you can expand more. So that state would be state 1, because we can go to node 3 from there. So we backtrack to node 1. From there, it's as simple as going down that green path on the diagram. No, we're not at a dead end, but we can go to a new state. So the new state would be node 3. So we can DFS to node 3. And same thing with node 2. That is invalid as well. So we backtrack back to a state that we can expand more. So we're back at 1. Same rule applies that happens each time you're at a problem state. Node 1 we can't expand more because we've figured out that each possible option is invalid. It's a definite no, we can't go any further. So node 1 is closed as well. We're back at node 0. So from node 0 we can go to node 1 or node 4. We're not going to go to node 1 because that's not going to work. That's a definite invalid solution that way. So we go to node 4. And at node 4 we're at the end, we figured it out. So did we solve G? Yes, we're done. And that's the end of DFS for backtracking. Another backtracking brute force example would be Groundhog Day. So with Groundhog Day, I've modeled it in the middle here. If anyone's seen the movie, they'd understand. So Bill Murray is a character, and he wakes up on the same day every single day. During the movie, he doesn't know why he's waking up, so I've modeled it as spend the day something new, and did I wake up on Feb 2 again? Yes or no, and then he goes back and loops through doing the day differently.
I studied 19th century French poetry.
What a waste of time.
I studied 19th century French poetry.
La fille qui j'aimerais.
You speak French?
Oui.
That's modeled as brute force only down the bottom, where he wakes up on Feb 2 and then he tries something new each time. And then the diagram to the right of the brute force diagram is a backtracking applicable diagram. that diagram has multiple partial solutions in the middle. For example, try something 1.0 or try something 1.1. Anything that's not a dead end is a partial solution which we can backtrack back to. In Groundhog Day, you can argue between both of them. You can say, well, he's just trying he's trying each day differently, and he's going back to waking up on the same day. He's only making one node of progress. It's not a partial solution. You can also argue that he's making progress towards figuring out what's the correct thing to do, which would be the backtracking applicable diagram. Either way, both are arguable, and only one of them is backtracking. Yep, next one. So when do I use backtracking? Backtracking can be used when you're approaching a problem with brute force and you can return to a partial solution as you're solving it. With the Sudoku problem on the left, you can see that the blue numbers filling up the white spots are partial solutions along the way. Even though not all of the white is filled up, you still have a partial solution to solving the Sudoku problem. Same thing with the maze on the right. As the mouse goes through the maze, it creates that green path that it thinks is the partial solution. And you can see it darts in, darts out, it's finding invalid solutions, and it backtracks back to where the last decision can be made. But those are both very good applications of backtracking. And why do I use backtracking? Why is it better than brute force alone or other methods? So in comparison to brute force, backtracking can reduce overall resources used when solving the problem. Two main resources being the memory used, so that's the amount of data you're storing while you're solving it. So when you're backtracking, you can keep those partial solutions in memory, which isn't normally done during brute force. So that can increase the amount of memory as well. Depending on how it's implemented, it can save memory usage as well, and it can be solved quicker as well. So when you're doing brute force, you have those massive time complexities, which you'll learn later on, but they take a long time. You're trying every option. Backtracking will reduce the amount of wasted time and wasted calculations done, so it can be quicker. And two optional benefits of backtracking is you can gain a partial solution while you're solving, and you can implement heuristics. You'll learn about heuristics next week, but both of those are not always applicable and they're not always needed. But the main thing to remember is that backtracking is usually quicker than brute force. So those are the examples I have for today. George has put up some examples with the Knights problem and some merge sort. With the study design as a guide to what you need to learn, it outlines tree search by backtracking and its applications and the general backtracking design pattern. If you've got those two down pat, you should be good. There's normally a backtracking question on the exam. None good enough to put on the slideshow, but I'll leave it at that. Thanks for watching the video, everyone. If you have any more questions, feel free to ask Georgia or one of the tutors, and we'd be happy to help.